addition to solving a polynomial equation by factoring, we also know how to solve an equation involving a power function by using the appropriate root property. When we're dealing with quadratic equations, the degree is 2, so we'll be using the even root property. And in fact, we're just going to say the square root. So we'll say the square root property because we're dealing specifically with index 2 when we're talking about quadratics. So this is the equation that we solved at the end of the previous video. X minus 4 squared is 9. And we can solve that by multiplying it out and then getting 0 on one side and then factoring. But we can solve this more directly using the square root property, namely x minus 4 is one of the square roots of 9. Right, we're just undoing squaring x minus 4, or in other words, plus or minus 3, which means adding 4 to both sides, x is 4 plus or minus 3. Our two possible solutions are x is 4 plus 3 is 7, or x is 4 minus 3 is 1. Of course, these are the same two solutions that we got by factoring. And of course, when we plug them in, they're still going to both work. 7 minus 4 squared, that's 3 squared is 9. 1 minus 4 squared, that's negative 3 squared, is also 9. Now, the big advantage that this method has over factoring, in addition to the fact that it's faster and easier if our equation is set up properly, is that we can use it to solve equations that we would not be able to solve by factoring. For example, suppose we wanted to solve the equation x plus 1 squared is 6. Right? We can multiply that out, right? X plus 1 times x plus 1 is 6. So x squared plus 2x plus 1 is 6. Subtracting 6 on both sides, we've got x squared plus 2x minus 5 equals 0. So our AC is negative 5. Our B is 2. Negative 5, the only way we can get that is 5 times negative 1, or negative 5 times 1. But 5 plus negative 1 is 4, which is not 2. And negative 5 plus 1 is negative 4, which is also not 2. So we can't factor. On the other hand, even though this polynomial is prime, there are solutions to this equation, and we can find those solutions easily using the square root property. So we have x plus 1 all squared is 6. In other words, x plus 1 is either the positive or negative square root of 6. X is negative 1 plus the square root of 6, or x is negative 1 minus the square root of 6. Now, how can we check this? Well, we can check this by plugging in, just expressed like this. Right? If we plug in negative 1 plus the square root of 6 plus 1, all squared, well, we'll have a negative 1 plus 1. Those will cancel out, and we'll be left with just the square root of 6 squared, which is 6. Negative 1 minus the square root of 6 plus 1, all squared. Negative 1 plus 1 cancels out, and we're just left with the square root of 6 squared, which again is 6. But that feels a little bit unsatisfying. We can also check by getting decimal approximations for these numbers. All right, so if x is -1 plus root 6, that's approximately equal to 1.449. And so we can plug in 1.449 plus 1 squared is 5.997601, which is very close to being 6. On the other hand, if x is -1 minus root 6, that's approximately equal to -3.449. And if we have -3.449 plus 1 squared, oh, that again gives us 5.997601, which is also approximately equal to 6. Now there's a problem. In order to use the square root property to solve, we need to have our equation written in the form of a power equation rather than as a polynomial equation. So far, we've just seen 2 examples that happened to be written that way. If we come across a quadratic equation in the wild, is it always going to be possible to write it as a power equation? It's going to turn out that it is possible, but we're not going to see why quite yet. In order to get to the point where we can see why this will always be possible, we're next going to talk about the graphs of quadratic functions.